to go for it. Thanks.
Thanks everyone for being here, and thanks to the organizers for putting this together and inviting me to speak. So I'm going to be telling you about infinite order rationally sliced knots, and everything that I talk about today is joint with Sungkyung Kang, JungHwan Park, and Matt Stoffregen. As I write these notes, if you want to like scroll back to something I've written, I just posted a link to Dropbox. It takes a minute or two to update, but it should work. All right. Great. So let me tell you what rationally sliced knots are. So first, let me remind you what it means for a knot to be sliced. So a knot K in S3 is sliced if it bounds a smooth, properly embedded disk in D4. And then using sliced knots, you can define the knot concordance group. Right, so this consists of knots in S3 under the operation of connected sum. Right, so this forms a monoid. The unknot is the identity, but for any non-trivial knot, you're missing inverses. One way to see that is the unknot is the only knot with genus 0, and genus is additive under connected sum. However, if you take this monoid and you mod out by the set of sliced knots, then you do get a group. The inverse of a knot is the reverse of its mirror image. So that's an exercise to check that K connects sum. The reverse of its mirror image is always sliced. So this is the knot concordance group. Okay, and so today I want to generalize this. So we say that a knot K in the 3-sphere is rationally sliced, which I'll denote Q slice. Okay, so if it bounds a smooth, properly embedded disk, not in B4, but now in a 4-manifold, it's the same rational homology as before. So with a rational homology, in a rational homology B4. Okay, so what's an example of such a knot? So for example, the figure 8 is rationally sliced. This is due to Finn, Tuschl, and Stern in the 80s. Okay, and so, well now, just like we did above, well, we can look at the set of knots in S3 under connected sum, modulo rationally sliced knots. And again, this is going to form a group. I'll denote this CQ. Okay. Notice, well, every sliced knot is rationally sliced since B4 itself is a rational homology ball. So we naturally get a surjection from the concordance group onto CQ. And then you could look at the kernel of this map, which I'll denote CQS. This is we have this short exact sequence, and well, this is just a subgroup of the concordance group consisting of rationally sliced knots. Okay, and in fact, the figure 8 is the first in an infinite family of rationally sliced knots. So let me give you some more examples of rationally sliced knots. So let's take this genus 1 surface and put n positive full twists in one band and n negative full twists in the other band. Okay. Right, so if n equals 1, this gives you the figure 8. Great, and so this whole family of knots is rationally sliced. This is due to Cha in 2007. And moreover, all of these knots are negative amphichiral, they're isotopic to the reverse of their mirror image. So all of these are order 2 in C, in the concordance group, right? If you're negative amphichiral, well, since the inverse of K is the reverse of its mirror image, well, then you're automatically order 2 in the concordance group. Okay, and so today I want to tell you about some more rationally sliced knots. In particular, I want to tell you the following theorem, joint with Kang, Park, and Stoffregen. Which is that there's a 3 infinite rank subgroup in the subgroup of rationally sliced knots. And I can tell you what it's generated by. It's generated by odd cables of the figure 8. So J is the figure 8. And the subscripts denote that we're taking the cable. And so, well, this is a non-trivial cable. So my notation for cabling is that the first parameter is a longitudinal winding and the second parameter is the linear winding. So I think of this as saying, well, odd cables of the figure 8 span an infinite rank subgroup of rationally sliced knots. Okay, and so, well, combining with the fact that Cha's examples are linearly independent in the concordance group, the following corollary, which is, as far as I know, the best known result about the structure of the subgroup of rationally sliced knots, which is that you have a Z infinity plus Z mod 2 to the infinity, a subgroup in here. Right, so to get this, we'll just take R knots and then take Cha's examples. Okay. And so, right, so I want to talk about this theorem today. And before I do that, let me just tell you a few remarks. So the theorem is false in higher dimensions. So I'll elaborate on that in a minute. Right, and so this theorem gives us the first examples of elements of infinite order in the subgroup of rationally sliced knots. And well, how do we prove this result? Well, the proof relies on bordered and involutive flow homology. Right, so bordered flow homology was defined by Lipschitz, Osbach, and Thurston. We use the reformulation of bordered flow in terms of immersed curves due to Hanselman, Rasmussen, and Watson. And then involutive flow was defined by Tristan Hendricks and Chipin Manilescu. And then with Ian Zemke, they proved sort of various useful properties about it. Are there any questions so far? Okay, so first let me sort of elaborate on what I mean when I said this is false in higher dimensions. Also, let me remind you of something called the algebraic concordance group. This is defined by Levine in the 60s. So I'll denote this with a math cal A. Right, so this consists of Seifert forms under the operation of direct sum, modulo metabolic forms. Wait,
Hey,
so
Jen, I don't know if it's my internet connection, but I can't see what you're writing right now. Do you see a difference?
Yeah, same for me. Nothing's updating. All right.
Yeah. I'm just going to stop sharing the screen and then restart. And
Sounds
hopefully-
good.
I fixed it on my end. Melissa's nodding, so hopefully I fixed it on her end too. If there's any other technical glitches, just speak up. Thanks. Great, so remember the Seifert form, right? So if you have your knot and you have a Seifert surface F, you can define this bilinear form on H1 of F. Right, you just take the linking number of a class X. Oh, sorry. So, right, if I want to take V of X comma Y, well, this is just the linking number of X with a positive push off of Y. Great. And what does it mean for a form to be metabolic? Well, it means that it vanishes on a half-dimensional subspace. And so it's an exercise to check that if your knot is sliced, well, then its Seifert form is metabolic. It basically follows from half lives, half dies in terms of each one of the three manifold boundary. Wait, and so so Levine was able to study this gadget, and he proved that it's isomorphic to z to the infinity plus v mod 2 to the infinity plus v mod 4 to the infinity. Great, and so, well, this infinite rank part, you can see that using signatures. So using Levine system signatures. Okay, and so then, well, you get this surjective homomorphism from the concordance group onto this algebraic concordance group. You just send the class of a knot to the class of its Seifert form. Great. So in the classical dimension, Casson and Gordon showed in the 70s that this kernel is non-trivial. They did this using what are now called Casson-Gordon invariants, looking at sort of these meta-abelian covers. Great. And this is in contrast to what happens in higher odd dimensions. So in higher odd dimensions, this map is actually an isomorphism. So this is an isomorphism in higher odd dimensions. In even dimensions, sort of everything is trivial. Right, so in odd dimensions, well, you can define the 2n plus 1 dimensional concordance group, where you look at knotted 2n plus 1 spheres in S 2n plus 3. Okay. Okay, and so, well, if a knot K is rationally sliced, then it's a result of Cha and Co that all of its signatures vanish. And so now I'm using Levine's result here. Well, this is going to imply that K is finite order in the n plus 2n plus 1 dimensional concordance group if n is greater than or equal to 1. Right, so the upshot is that in higher dimensions, if you're rationally sliced, well, then all your signatures vanish. And then, well, using this fact this is an isomorphism in higher dimensions, it tells you that you have to be finite ordered. So in higher dimensions, any rationally sliced knot is finite order, and that's in contrast to what happens in the classical dimension, where we're able to find lots of rationally sliced knots that are infinite order. Any questions? Okay. So let me give you some more ways to build rationally sliced knots. So we say that a knot K is strongly negatively amphichiral. If there exists and orientation and involution, orientation, reverse, and involution from S3 to itself, such that phi of k is k. Right, so negative amphichiral means that k is isotopic to the reverse of its mirror image, and strongly negative amphichiral basically means that you can realize that via an involution of S3. And so in 2009, Kawauchi proved that if K is concordant to a strongly negative amphichiral knot, then K is rational slice. All right, so let me sketch the proof of this for you. Okay, so we might as well assume that K itself is strongly negative amphichiral. So let's assume that K is strongly negatively amphichiral via an involution phi. Okay, and then you can check that this involution phi, well, this induces a 6.3 involution on the zero surgery along K. So I'll denote this phi tilde. Okay, and so we can quotient by this action. So let's call Y the zero surgery along our knot K, modded out by this 6.3 involution. All right, and so now let's take the twisted I bundle over Y, or equivalently, this is the mapping cylinder of this double cover. Okay, and so now what can you check? You can check that the boundary of this is just the zero surgery along K. Okay, so let me draw a schematic. So we have this twisted I bundle over Y. Its boundary is zero surgery along K. So now we can attach a two handle that basically, like, I think of it as like undoing the surgery along K. So you can attach a two handle to get back to S3. So this is a two handle. And so now the boundary is S3. And then it's an exercise for you to check that here's their knot K, and that the co-core of this two handle is a slice disk for K, and that the resultant three manifold is a rational homology ball. So I'll leave it as an exercise for you to check that this is a rational homology ball, and that K bounds the co-core of the two handle. All right, so that's a sketch of Kawauchi's result. Right, so Kawauchi's result is that if you're strongly negative amphichiral, then you're rationally sliced. And so a natural question would be, well, is the converse true? If you're rationally sliced, then are you strongly negative amphichiral? And well, corollary of our theorem is that the answer is no. So corollary of our theorem is that the converse to Kawauchi's result is false. Right, since we give an infinite family of rationally sliced knots that are infinite orders, in particular, they can't be negative amphichiral. Any questions? Okay. So now I want to talk about the proof for our theorem, right? So the proof of the theorem relies on,
Jen, I think your screen has stopped updating again.
oh, thanks, Samantha. Yeah, I don't have a better solution than to just stop sharing and start sharing again. If anyone has any better solutions, let me know. This hasn't happened before me with Zoom. Okay. Thanks. Okay. So the proof relies on Heegaard Floer homology. We use Heegaard Floer to do this computation of the knot flow complex of these odd cables of the figure 8. So throughout today, J is going to be the figure 8. Great. And then use involutive Floer homology to show that these examples are infinite order. All right. Okay, so I'm going to mostly black box the Heegaard Floer part, but I'm going to sort of tell you what the formal structure of the invariants that we're going to be using. So we'll consider what I'll call CFK of K. So this is the knot flow complex associated to K. What type of object is this? This is a finitely generated bigraded chain complex over a polynomial ring in 2 variables. So F are joined U, V. So F is just the field of 2 elements, and U and V are just 2 formal variables. Right, so these things are defined in terms of a doubly pointed Heegaard diagram, and so you're counting some pseudo-holomorphic disks, and you should think about one of your variables counts how many times you cross your first base point, and the other variable counts how many times you cross your second base point. So as an example, right, so here's a doubly pointed Heegaard diagram. This is, turns out this is the one of the trefoils. You have these intersection points that are going to be your generators. And then, well, this disk here, it's a disk from B to A that crosses W. So that we count how many times it crosses W with the variable U. And then this disk here is a disk from B to C that crosses Z. And so we'll count that with the V. Great. And so sort of I'll draw this, and sort of what this is trying to pictorially tell you is that the boundary of B is UA plus VC. And I sort of picture this ring here. I picture this ring here as sort of 1 sits here, and then U moves you one place to the left, V moves you down, and then, well, UV will move you diagonally. So that's sort of how I decided how to draw this. Right, and then the boundary of A is 0, and so is the boundary of C. And then sometimes for shorthand, instead of actually drawing all these labels, I might just draw this like this. Okay. But anyway, so the point is that the knot flow complex, it's this bigraded chain complex over a polynomial ring in 2 variables, and you can represent these 2 variables sort of graphically, and then you get these little pictures that represent these chain complexes. Wait, and so the and so earlier incarnations of this the knot flow complex often have this filtered chain complex. But if you work over this polynomial ring in two variables, you sort of encode all the information of the filtration in terms of the second variable. So there's no filtration in this perspective. You just have this chain complex over this polynomial ring in two variables. And the chain homotopy type of this chain complex is an invariant of your knot. This is all due to Oshoff and Szabo. But if you're interested in concordance, well, you might ask, well, what part of this chain complex is actually a concordance invariant? And so one potential answer to that question is this thing, which we'll call CFK connected. So this is a concordance invariant. You should think of this as the summand of the knot floor complex that supports the localized homology. So supports the homology when you invert U and V. Yeah, so this idea of CFK connected, it was sort of implicitly defined in work of myself, also work of Ian Zemke. It's sort of the concordance analog of some homology cobordism work due to Matt Stoffregen in the pin 2 setting, in the pin 2 monopole setting, or by Kristen Hendricks, myself, and Ty Lidman in the involutive Heegaard Floer setting. And then it was sort of written down in the knot floor setting by Heegaard Floer. So you have this concordance invariant, and you can sort of see it in terms of these pictures. So let me give you some examples. So let's consider the trefoil connexum itself. Right, so it's knot floor complex looks like this, right? So this is sort of the analog of this picture. Okay, and now if you want to see what CFK connected for this knot looks like, well, it turns out it's the part that supports the localized homology. So it's this zigzaggy part right here. So that's CFK connected for the trefoil connexum itself. Let's look at another example. So let's look at the figure 8. The knot floor complex for the figure 8, which I'll call J, consists of this single dot and then this box here. And so the part of this, the summand of this that supports the localized homology, well, that's actually just this dot right here. So that's what CFK connected looks like for this example. And now let's look at 2 more examples. So let's look at the 2 - 1 cable of the figure 8. So this, you get these 2 boxes and you get this single generator. And so CFK connected is just this single generator. And then let's also look at the 3 - 1 cable of the figure 8. You get sort of 2 long skinny boxes and then this sort of L-shaped piece and a single generator. And then again, CFK connected is just this single thing here. Okay. So, right. So I defined
Jen, sorry. This might be a very elementary question. The word connected, is it just because it's always the piece that's connected to the generator for S3? Or is that just?
So we use the word because Matt Stoffregen used that word. And yeah, it's the stuff that's sort of, yeah, it's all the stuff that's like connected to this part here, is the way I think about it.
Okay.
Right, it's sort of connected by like the differential to this localized homology here. Yeah, that's a good question.
Thank you.
With actual topology, there's an interpretation in terms of that.
Oh, wait, Kristen, can you speak up?
Matt's work was with actual topology, and you can think about connectedness in terms of things being sort of near the fixed set and when you have an actual space involved.
Thanks. That's a good answer. Okay. So I gave you sort of this hand wavy definition. Let me give you a more rigorous definition of what CFK connected is. So the formal definition. Okay. Right. So knot flow homology is a TQFT. So when you have a concordance between two knots, it induces a map on their knot flow complexes. Well, a local map F from the knot flow complex of K1 to the knot flow complex of K2 is a FUV equivariant chain map such that F star is an isomorphism on this localized homology. And right, so this is an algebraic definition, but the point is that these maps induced by concordances, they satisfy this property. So in particular, well, if K1 is concordant to K2, then there exists a local map F from the knot flow complex of K1, the knot flow complex of K2. This is just induced by the concordance. And then a self-local map, it's just a local map that's a endomorphism. So it's a local map F from the knot flow complex of K back to itself. All right, and so the game is you want to find like the smallest part of this chain complex that like is invariant under concordance. So if you want to find the smallest part of that, well, what do? You look at self-local maps and you look for the one with the biggest kernel. If you have the biggest kernel, well, the image is going to be like as small as possible. So we say that a self-local map F is called maximal if for all self-local maps G, the kernel of G is a subset of the kernel of F. Right, so you should just think of this as saying, well, a self-local map is maximal if it has the biggest possible kernel. Right? If any other self-local map there's kernels contained in there. So you want to find the self-local map F with the biggest kernel, so the one that has the smallest image, but that still has this property that it's an isomorphism on the localized homology. And sort of this algebraic framework does what we wanted to do up here. It sort of picks out like the smallest summand that supports the localized homology. Because you're finding the biggest kernel. So you quotient out by the biggest kernel, you get sort of the smallest thing that sort of contains the information that you wanted. And so CFK connected, it's just defined to be the image of F, where F is any maximal self-local equivalence. Great. So it's an exercise to check whether this is actually well defined. As long as your self-local equivalence is maximal, it's independent of the choice of self-local equivalence. And that what this actually does is it picks out the summand that like supports, it picks out the smallest summand that supports the localized homology. Okay, so this is one way to try to get out as much concordance information as possible from the knot flow complex. Okay, so this sounds like good news. However, there's a result of Oswald and Zaba, which says that if K is rationally sliced, CFK connected is going to be trivial. So trivial in the sense that it's going to be the same as CFK connected for the unknot. Great. So what is this saying? This is saying that if you want to study rationally spliced knots, well, this formulation of the connected knot flow complex isn't going to help you. So this might sound like bad news, but really what it's saying is, well, we just need some additional structure. And to get some additional structure, well, then we'd be happy. So really the upshot is that we need additional structure. Great. And well, as luck will have it, Kristen and Cyprian put extra structure on the whole Heegaard Floer package when they defined involutive Heegaard Floer homology. So this additional structure exists. This is why we need involutive. Involutive. Right, so this is due to Hendricks and Manilescu. Right, and so what's the trick that makes involutive actually help in this situation? The trick is that involutive gives us an invariant of concordances in spin rational homology cobordisms. So it's this bit that that really sort of makes things work for us. Okay, so in terms of the knot flow complex, what does this extra structure look like? Well, we get this endomorphism iota k from the knot flow complex to itself. What kind of map is this? Well, this is skew equivariant. So basically it just swaps the actions of U and V. That's what skew means in this context. And then in the knot setting, iota k is not actually an involution. It turns out that it squares to be this a certain map called the Sharkar map. It's not so necessary for today's talk what exactly this is. Just the point is that this endomorphism squares to be homotopic to something that we know. Okay. Great. So we have this map iota k on the knot flow complex, and I'm going to tell you the very rough philosophy, which completely lacks vigor, but it sort of tells you how we're able to find these examples. So this very rough philosophy is not rigorous at all, but it gives you an idea of how we actually came across these examples. So the very rough philosophy is that iota k pairs up symmetric summands in the knot flow complex. And then you might get things that like don't have a sort of symmetric friend. So then there's these unpaired summands. And these unpaired summands may be sort of intertwined with CFK connected by iota k. And so then this extra structure makes it possible to define a more robust invariant, which I'll call CFK iota k connected. It's maybe not the best, doesn't quite roll off the tongue, but it's sort of is descriptive of what it is. And so this is, well, this consists of the connected complex plus possibly these unpaired summands that are intertwined via iota k. So this is plus summands that are intertwined with CFK connected by iota k. Okay. And so then the point is that this thing is a concordance invariant. It's an invariant, just like, right, so it's an invariant of concordances and spin rational homology concordance, since it depends on an involutive. Okay, so this is sort of the very rough philosophy. Okay, so now let's make this more rigorous. So to make it more rigorous, what do? I'm going to scroll up. We just take, okay, let's just take this entire definition here, and let's just add in iota k everywhere that it like makes sense. So I'm just going to take the old definition. Oops. And then I'm just going to paste it here. I guess I need a new page. Okay. So the game will be to just add in iota everywhere that it makes sense to. Okay, so let's call this an iota k local map. Well, okay, we wanted to satisfy the same properties as before, but we also wanted to play nicely with respect to iota. So, well, you might think that should mean that it should commute with iota, that f should commute with iota k, and you'd be right, except everything's really up to homotopy. So let's say that this, so f iota k1 should be homotopic to iota k2 f. Okay, so I've added iota k here and I've added this here. And then, well, if two knots are concordant, then there is an iota k local map. And then an iota k self-local equivalence is an iota k local map from not flow complex to itself. And then, well, I mean, we're basically just adding iota k everywhere it makes sense to our old definition. And then CFK iota k connected is just the image of any maximal iota k self-local equivalence. Great. So sort of basically the only like change in the definition was here is just that we required this our map to commute with iota k up to homotopy. And then all the other definitions just follow through as before. But it turns out, so this is the only real change that we added was that these maps have to commute up to homotopy with iota k. But it turns out this gives us more information. So let's look at some examples. Okay, so let's look at the same examples as before. So we have the trefoil connects on itself. So we have this sort of staircase piece and we have this box. And it turns out that if you were to actually compute iota k for this example, that iota k sort of sends some stuff from the box into some stuff here, maybe vice versa. But the point is that these two summands get intertwined by iota k. And so they wanted to see what CFK connected is for this knot. It's actually the whole thing. It's both this staircase and this box. You could also look at the figure 8, which was the single generator in this box. And in this example, again, CFK connected is the whole thing because iota k sort of sends this thing to mixes all this stuff up. All right. Now let's look at the 2, -1 cable of the figure 8, which I told you had the single generator and then this box here and then this rectangle here. And so what does iota k do in this example? Well, iota k sort of just like kind of swaps these two boxes in some sense. And this thing generator hangs out by itself. So these two sort of get paired up by iota k. And so the iota k connected complex is just the single generator for the 2, -1 cable of the figure 8. And this is in contrast. Should let me give myself some more space. So this is in contrast to what happens for the 3-1 cable of the figure 8. So for the 3-1 cable, you get these, let's say, of these two rectangles. Then you get this this other part here, and then the single generator here. And the part that I've drawn in blue is the iota K connected part. So what does iota K do in this example? It basically pairs up these two pieces, but then this part here gets intertwined with this. And so CFK, the iota K connected part consists of this part and this. Because this part is sort of unpaired, and it turns out it gets intertwined with this single generator. Great. So I've shown you these two cables of the figure 8, and sort of this pattern persists. So for any even cable of the figure 8, you get an even number of these boxes that get paired up by iota K. And for any odd cable of the figure 8, you get sort of an odd number of things, and sort of the odd part out gets connected to the single generator. Okay, and so that was the computation that we did using border floor homology and involutive. So we have the following proposition, which is that the iota K connected complex for these odd cables of the figure 8, you get this sort of L-shaped piece that looks like this, and you get the single generator. So this length here is 1, this length here is n-1, and this length here is n. Wait, so how did we do this computation? That's how the computation relies on, there's this cabling formula due to Hanselman and Watson using immersed curves.
I think it froze again,
Oh,
sorry.
it froze again. It's okay. Okay. Okay, there it is. That's what we see now. Thanks. Okay. Okay, so this cabling formula is in terms of immersed curves. It turns out we need a little bit of grading information. So we actually get some grading data from work of Ina Petkova. Great. So for the experts in the audience, this cabling formula only gives us information over F adjoin UV mod U times V. But it turns out that sort of that's enough. We're able to lift this to just this ring. And then, okay, well, how do we compute iota K? Well, we're able to do a partial computation of iota K using formal properties. So we use the fact that iota K is skew graded. We use the fact that it squares to be the Shar-Car map, and we use the fact that it's a chain map, and sort of that's enough for us to compute enough of iota K in order to prove this proposition. So in some sense, we got kind of lucky in the sense that there's not like a general way to compute all of iota K for like cables even, let alone like general satellites. But in this special case, we got lucky and were able to use formal properties to sort of cobble together enough to get the result that we wanted. Great, so we computed the iota K connected complex, and then, well, how do we show, right? So we're able to show that these knots are infinite order in the concordance group. So we need some property about connected sums. So the knot floor complex behaves nicely under connected sum. Basically, the knot floor complex of the connected sum of two knots is the tensor product of their knot floor complexes. And so in the appropriate sense, the same thing holds for involutive. So I'll kind of cheat and I'll just say that you want the involutive iota of the connected sum of two knots. Well, it's the tensor product, as long as you interpret the tensor product in the appropriate way. So I'll kind of just cheat and write it like this.
I'm so terribly sorry, but I can't see what you're writing again.
Okay.
I'm so sorry.
I'm really sorry. I don't know why.
I think it's just Wi-Fi and stuff. Yeah.
Okay. Yeah.
We'll just pretend this is like board erasing time in real life.
Yeah. Okay.
Beautiful.
Hopefully this will be the last time in this talk that this happens, but maybe it won't be. Great. Okay. So these things behave in some controlled way under connected sum with some appropriate tensor product in this setting. And then basically, right, so for these, we have, look at all of these odd tables of the figure 8, we get sort of this length n thing here that depends on the cabling parameter. And so like the very rough idea is that, well, when you take these tensor products of these things, you have this length n part here. And then so this length n part sort of persists under tensor product. And that's what gives us linear independence. You just sort of do this tensor product thing and you see that we get these like length n things kind of stick around, and then you can show that this family of things are linearly independent. Great. So that's the main idea of the proof. So let me conclude with a few sort of open questions. So further questions. Right, so notice it was very important for our techniques that we were using these odd cables of the figure 8, because those odd cables sort of gave us a sort of odd piece out that then gave us this non-trivial iota k connected. And so it'd be really interesting if you could say the same thing for even cables of the figure 8. So why would that be interesting? Right, so maybe you look at these even cables. So are these even cables sliced? Why is this question particularly interesting? So remember the figure 8 is sliced, and so any cable of the figure 8's not sliced. The figure 8 is fibered, so any cable of the figure 8 is also fibered, and sort of the fibration sort of gives you some extra things to work with. In particular, Miyazaki was able to show that these even cables of the figure 8 are not ribbon. So I guess if you believe in the slice ribbon conjecture, well, you would suspect that these things are not even sliced, or maybe you don't even believe in the slice ribbon conjecture, but maybe you just think that a counterexample would have to be really hard. So if you think a counterexample would have to be really hard, that would still lead you to conclude that the answer to this question is that no, these knots are not sliced. That'd be really interesting to prove. What are some other interesting questions? Well, right, so the figure 8 is rationally sliced. You might ask, well, what is the first homology of the rational homology ball in which it is sliced? H1 of that rational homology ball is Z mod 2. Great, and so in particular, all known examples of rationally sliced knots found in Z mod P homology balls where P is odd. Right, so remember, like a Z mod 3 homology ball, like if H1 is Z mod 2, then that's a Z mod 3 homology ball. Anyway, it always takes me a minute to remember that. And right, and so the figure 8 is sliced in a homology ball of H1 Z mod 2. And so our examples, oh, I never said why our examples are rationally sliced. Right, so the figure 8 is rationally sliced. That's due to Fintuschel-Stern. And then if you take a cable of a rationally sliced knot, that's going to be rationally sliced. You basically cable the slice disk. Wait. So it'd be, you're right. So all known examples of rationally sliced knots found in Z mod P homology balls, where P is odd. And so, well, an open question, does there exist a knot K that's not sliced in B4, but is sliced in, say, a Z mod 2 homology 4 ball? So that would be pretty interesting. Okay. What would be even more interesting is if you found something that was not sliced in B4, but was sliced in an integer homology ball. And then I guess what would be really interesting is to find something that's not sliced in B4, but is sliced in a homotopy B4. Wait. So those are some open questions that I'd love to hear the answer to. So hopefully at some future iteration of the Georgia Topology Conference, one of you will give a talk answer these questions that I just outlined. Great. Thanks for your time.
Thank you, Jen. Any questions?
Yeah, is there anything known about relations between rational slicedness and concordance and the topological category?
Oh, that's a great question that I haven't thought about. There's possibly people in the audience who know a lot more about the topological category than I do.
Is there a kind of a simple example where the complex isn't symmetric, but the pieces don't get intertwined?
Oh, yes. Right, so you have this complex for the figure 8, where you have this 1x1 box. You could just imagine you have that, but instead of a 1x1 box, you have a 2x2 box. That one won't get intertwined, but I think that might actually just be a feature of the fact that we're working over Z mod 2 coefficients. If you were able to do all this over Z, then I think the expectation is that it would be intertwined, but good luck trying to do this over Z. But the expectation would be that, yeah, it kind of gets stuck on.
Thank you.
Is it easy for you to briefly verbally describe how you use Heegaard Floer homology to show like the difference between like J2 -1 and J3 -1 or J3
yeah.
5 or something?
Yeah. So there's right. So this Hanselman-Watson formula, if you want to take like a P(1) cable of a thing, at some step you just draw P copies of the complex.
Okay.
If P is odd, you get an odd number of things, and if P is even, you get an even number of things. And then when you do the computation for iota K, you have an even number of things. They all get. We didn't actually do the computation, but we expected that I checked it roughly. Anyway, yeah. So for even things, they sort of all get paired up. But if it's odd, there's an odd number of things, and you can show that the odd thing kind of gets stuck onto the connected complex.
Okay, thank you.
If there is no other questions, let's thank Jen again. We'll stop